But in principle, of course, you could have a lot of different arms or treatments. You could allocate people to 5 different groups, for example, or 5 different treatments. And so when you have these multiple what are called arms or treatments in the multi-armed bandit problem, then there is this key trade-off, which is the exploration versus the exploitation trade-off. Because there are 2 objectives that you have to balance. On one hand, your primary objective is to maximize the reward, right? That you get from interacting in this. Basically, the reward here is the probability of success that you get as a result of, for example, in the case of medical sort of clinical trials, the reward will be the success of the drug in removing the disease, let's say. So you want to maximize that probability. But in order to do that, you have to explore the environment, because the reward probabilities of the various treatments that you're considering in a medical trial, in a clinical trial, for example, are not known. You don't know the probability of success of various drugs. That's what you're trying to learn. So let's say there are 5 drugs under consideration. So you have to test people, right, with all those drugs, and you have to allocate people to the treatment group, which in this case will be allocation of a particular person to a certain drug and testing him with that drug. You have to do that in order to learn about the probability of success of that drug. But there's a trade-off, because there's some uncertainty involved here, and there's a risk that, if you allocate, that drug may not be that good, and therefore it has a very small probability of success. And so when you test people, you don't get any success. But what you wanted to maximize was your rewards over time. So you've lost an opportunity to maximize your reward. So that's called the exploration trade-off. Because on one hand, you want to explore all of these different treatments by allocating people to these different treatments. Because only if you allocate people to a certain treatment and observe the outcome can you learn something about the true probability of success of that treatment, right? So you want to explore, because exploration can help you discover the optimal, what is known as the most optimal arm with the highest reward probability, or the drug with the highest success probability, and so on. But there's the trade-off that if you explore too much, you also don't want to explore too much, because if you explore too much, you lose on exploitation. So what's exploitation? Exploitation is the idea that based on your experience so far, because remember, we're interacting with the environment in a dynamic context in the case of bandit problems. So based on, let's say you had capital T time period so far of experimentation, you know that a certain drug which does really well because you tested it, let's say, T minus 1 times, and you've only tested some other drug only once, or any of the other drugs only once. So you know a lot about the probability. You have a pretty precise estimate of the probability of success of the drug which you tried most often or most frequently in the past. And if the probability is good enough, let's say it's 70% success, you want to keep on allocating people to that drug, because it's giving a pretty high reward probability, and that is called exploitation. Because you want to exploit whatever information you have right now about what is the best possible arm. So you want to do that also. And if you do too much exploration, you may be allocating treatments to drugs which have a very low probability, let's say 10% or 20%. So you're losing so the opportunity cost is that you already know that this treatment, which you've been experimenting with a lot, has a very high probability, but you're losing on that. But on the other hand, there might exist some other treatment out there which has a 90% probability of success, which is even better than the current treatment, for which you have relatively precise estimate that the probability is somewhere around 70% with a small confidence interval. So you also want to explore, because you may explore better options, because you don't know, because since you haven't explored other options, you don't know that whether you can find a better option or not. A classic sort of everyday example of this is sort of what is called the restaurant example. So let's say you are going out for dinner and there are 2 restaurants. One of them is the restaurant that you've been going to for, like, say, years, and the quality of the food is pretty good there. And so you could just, play the safe option and just go there, right? And you're guaranteed a certain level of satisfaction with a very high probability, with very small sort of noise, with a very sort of narrow confidence interval. On the other hand, you also want to explore other options, because it may be that you discover a restaurant which is even better. But there's a risk that if you explore too much, you also have to tolerate a lot of bad food. So that is the key sort of exploration-exploitation trade-off which arises in multi-armed bandit problems. Yeah, so as I said, you reevaluate these assignment probabilities to all of these treatments over time, and you're dynamically interacting over time. And as you keep on sort of allocating more and more experiments, more and more treatments, more and more individuals to these treatments, based on your experience over time, you keep on learning about these probabilities and updating them over time. And initially, you may be thinking that a certain treatment A is like a really good treatment because that has a very high probability of success. But as you explore other options, you may actually change your opinion because you're updating these probabilities. So notice that in the traditional sort of A/B testing, we don't update probabilities. So there's someone is trying to raise a hand, but we've decided that we'll take the questions only towards the end. So you can note it down, and towards the end, we'll sort of enable the chat, and then you can ask the questions. Right. So the key point is that you're reevaluating these probabilities of rewards or success probabilities of all these treatments over time, and you're learning over time. And this is not the same thing as a traditional experimental design in which you're not learning anything over time, and you just decided that 50% of 50% of the time you're going to go to restaurant A versus 50% of the time you're going to go to restaurant B, for example. So if you want to think about it sort of more sort of intuitively, I have this picture here from a casino. So the reason why the name of the topic for this lecture is called a multi-armed bandit problem is that in casinos you have what are called bandits. So in this case, you just have two arms, but in general, you could have K number of arms. Or in casinos, you also have a single armed bandit as well. But if you just have a single armed bandit, well, it's actually still an interesting problem, but it's not that interesting. But the key sort of issues arise when you have multiple sort of bandits, because then you want to decide which one you want to allocate. So in this casino, you have this two-armed bandit, which you can, I hope, see on the screen. So you could either decide to pull the lever on the right-hand side, or you could decide to pull the lever on the left-hand side, right? So, and the idea is that the reward probabilities are not known. So you don't know there's a certain probability P1 with which you get a reward. Let's say it's just a binomial thing. So you either get a reward of 1 of a fixed size, or you don't get anything. But the reward probability or the probability of success in these sort of binomial trials are not known. So it may be that the right lever gives you a probability of success of 70%, but it may also be that it gives a very low probability and so on. And similarly, you don't know the reward probability of the left lever. So in the multi-armed bandit problem, what we're trying to do is to try to optimally experiment over time and decide the optimal allocation, in this case, optimal interaction with the arms. So let's say if it is true that the probability of success is 90% of the right arm and 10% of the left arm, you want to allocate, let's say, and if you're solving a finite horizon problem for capital T periods, you want to allocate in each period for all the capital T periods, the right arm, right? Because that's what's optimal. That is what is going to maximize your expected reward over this finite horizon. And similarly, you might want to allocate only to the left and so on. If both give a probability which is equal to each other, then you might be indifferent between mixing as well, which is what we call a mixed strategy in game theory. So that's what's happening here. But the problem is that you don't know these reward probabilities. If you knew them, then the problem is solved. That's why this is a problem. So you have to learn over time as you keep on experimenting and you keep on pulling the right lever. It gives you some really good outcomes, and you may be motivated to continue to use the right lever. But you also don't want to lose out on the opportunity to experiment with the left lever, because it may be the left lever is even better. And similarly, because there's some uncertainty involved here. This is a probability distribution, right? So there is going to be a small probability, but non-zero, that you'll get like very bad sort of draws. So maybe that you're unlucky. Maybe you just had an unlucky sort of, a sequence of draws when you were pulling the right lever for the first 5 times, and you got all failures, just like you roll a dice. But that doesn't mean the probability of success is very low. It could be that you were just unlucky. So therefore, these kind of trade-offs arise, and the objective of the multi-arm problem is to do optimal treatment allocation over time. This is known as adaptive treatment allocation over time, because you're adapting over time to the information that you're getting. And the information here, remember, is what? There are 2 sets of information. One is that you know which action you took at time t, which is whether you pull the right lever or the left lever. And the second information is that once you did that, remember I said in bandit problems, you get an immediate sort of information regarding the outcome. So you know whether, what sort of outcome you're going to get immediately in this case. Right? A more general example is that you could have any number of bandits, right? In this case, you have 6 bandits. Sorry, it's not 6 bandits. I'm sorry. 6 arms. These are called arms of the bandit. I come back to this particular graph, and there's actually a reason why you have these beta distributions showing up in green corresponding to all of these arms. And I'll come to why I have these beta distributions here once I've defined these things formally. And I'll come back to this particular graph. But that's what a bandit problem is. Over time, you have to decide at any given point in time whether you want to choose arm A, arm B, arm C, arm D, arm E, or F. And over time, you have to optimally design the path of decisions that you're taking over time. And yeah. And since you don't know the reward probability, since you don't know the reward distributions corresponding to all these arms, there is going to be an exploration trade-off. So you want to explore all the arms so that you learn about all of them, just in case, and because you want to discover the optimal arm with the highest reward probability. But you also don't want to explore too much, because based on the information so far, if let's say arm D has a very high probability, that you want to keep on exploiting your given information up to this point also. If you explore too much, you lose on a lot of rewards. So that's the really key idea. This has applications in design of online experiments, online advertising, dynamic online pricing. So for example, Amazon and a lot of other companies, Google and so on, they have online pricing, and they are sort of pricing millions of products, and there are millions of transactions per day, and in a very short period of time. And they have the possibility of price discriminating, so that they can charge different prices to different individuals over time based on the characteristics that they observe and so on. And this is happening over time. And what they observe is that if they charge a certain price, does this person actually buy the product or not? So bandit problems are applied in designing dynamic pricing in the context of online e-commerce, online platforms, commercial platforms such as e-commerce. You could also use them in stock investment if you have portfolio decisions regarding your financial decisions. In this case, the arms would be the various assets that you want to invest in, and the decision is how frequently you want to invest in each one of those assets, and so on. I already discussed clinical trials and medication dosing problems. And of course, the dynamic pricing is already an economic example. And I have another very interesting economic policy design application from a 2020 paper, which has not even yet been published. And I came to know about this paper because I studied a course from one of these co-authors. And I think this is a really amazing paper. And I anticipate that this will probably be published in AER in the next year. So it's not even published yet. So this is like, they're still working on it, but they have a working paper on their websites, which is freely available, which is why I have it cited over here. Right. So I'll come to formally defining a bandit problem. I've discussed, I think, in quite a lot of depth, the intuition. So formally, a multi-armed bandit problem with more than one arms is just a tuple of these two objects, A and R. So what's A? This curly A is just a set of actions, set of possible actions that you could take, or in other words, just like the set of possible arms. So if you have five arms, the decision could be either to interact with arm 1, 2, 3, 4, or 5. So that's just a set A. The second object is the curly R, which is nothing but the reward distribution. So the reward distribution across all these actions, which is not known to you, but that is what is going to define the multi-armed bandit problem. Now, each action, small a, which belongs in the set of all possible actions, refers to, as I said, interaction with one arm, which in the case of the casino bandit will just be to pull the arm, right? So if you take action A, which is a particular action A, it means you're interacting with a particular arm outside from the set of possible arms. And this Q of A is called the action value function. This is nothing but the expected value of the reward, and this depends on the reward distribution, right? This is just the expected value of small r, which is just a reward conditioned on the fact that you have interacted with a particular arm A, right? And this is equal to theta, where theta is we're just talking about Bernoulli kind of trials here. So there are k possible arms in general, capital K number of arms in the multi-armed bandit problem. So the cardinality of this set is k, for those of you who are interested in math. And then the probability theta belongs in this, it could either be theta 1, theta 2, all the way to theta capital K. These are the k reward probabilities of these capital K number of arms. And depending on what arm or which action you've taken, you'll have a different probability of success. But these are not known to you. But these exist out there, but they're not known to you. So obviously the expected value of the reward is equal to theta. Because here the reward is, as I said, just a binary reward. So the expected value of the reward is theta times 1 plus 1 minus theta times 0. With probability theta, you get a reward of 1. With probability 0, you get a reward. With probability 1 minus theta, you get a reward of 0. So obviously, the expected value of the reward is just theta. What is R? R is just a reward function. So the, if you evaluate the reward function at small r for any given action AT, where AT is just the action that you've taken at time t. Because remember, we're interacting over time, and we're taking these different actions over time. So this thing just means that I'm evaluating the reward function at small r for action AT. This will just give me the probability that capital R is equal to small r, which just means that the probability the reward that you get is going to be equal to R, conditional on the fact that the action that you've taken is AT, which is some particular action that you've taken. And this obviously is the reward distribution, conditional on the action AT. What's your goal? The goal in the finite horizon case, where you have capital T is the finite horizon, and here I don't have any discounting for simplicity, is just to maximize the sum of these rewards, right? Which makes a lot of sense. And remember, this reward is, it makes a lot of sense. You just want to maximize the number of rewards, or rather expected rewards, because you don't know what these rewards are. But the idea is that you don't know what these rewards are, right? You can only form an expectation regarding them through the Q function, which is known as the action value function, because you don't know what the rewards are ex ante. You know them ex post, but you don't know them ex ante. So let's say that exists out there some arm of this bandit problem. You don't know which one it is, but there is definitely going to exist some arm out there which has the highest expected value of the reward, right? Or the highest probability of reward. So let's say this arm is A star. You don't know what A star is, and that is what you're trying to discover over time. That's the objective of the bandit problem. But it exists out there, so we can define it. So A star is just the optimal arm. And what is A star? It is just the maximum value of Q of A across all the possible actions. It is the action that if you choose that action, it maximizes your action value function, or Q of A, which is just, remember, just the expected value of the reward. So it is just the particular arm A star, which is the most optimal arm, or it has the highest expected value of the reward. And we just call the value of the reward V star, which is just Q of A star. And this is the maximum possible expected reward that you could get across all these arms. If you knew what A star was, you would just play A star all the time. The problem is that you don't know what A star is, so your actions AT may not be equal to A star, and over time you're exploring and exploiting and so on. You're choosing different decisions, and you have a whole sequence of AT where A1, A2, all the way to A capital T is a sequence of actions that you're taking over time. Some of those actions may actually be equal to A star. You may accidentally select the right arm, and some of them may not be equal to A star, right? So there will be this deviation between V star, which is the maximum possible value of the reward that you could get, or the maximum possible expected reward, and Q of AT, which is over time from T1 to capital T, which is a horizon, where all of these are decisions that you've taken over time. So in some cases, this difference will be equal to 0 if AT is equal to A star. In other cases, this will always be positive, but this will never be negative, because V star is the maximum, and you simply add them up. You have to take an expectation, because you don't know what V star is, and you don't know what, and at time T, if you're trying to evaluate your regret, you also don't know what sort of decisions you'll be taking over time. So this is your total regret, or the expected value. We call this a regret, because if you chose some action A bar, which is not equal to A star, and it gives you something lower, then V star minus Q of AT will be positive, right? So this is sort of like an opportunity cost, or like a positive regret, because you regret that you did not choose the optimal action A star. And you chose something which is suboptimal. So this is called the regret, or this is the total regret. And the objective of the, so it turns out maximizing the sum of rewards is equivalent to minimizing the total regret. And this is more convenient to work with because of technical reasons. So the formal analysis of multi-arm bandit problems works with trying to find algorithms which will minimize the total regret, which is this thing. Now, the thing is that regret is going to increase over time, right? Because unless at a particular trial you were choosing AT equal to A star, then this particular, the marginal addition to the total regret is going to be 0 as a result of that particular trial or interaction with a particular arm or decision or action. But otherwise, obviously regret is going to increase over time. So it's going to be some sort of increasing function in time right? On the y-axis, if you have regret, it's going to be some sort of increasing function. It may have some flat portions, but it's going to be increasing over time. Now, the objective of the algorithm is to find an objective of this analysis is to find an algorithm which is going to lead to a regret, which has a sort of concave or sublinear kind of rate of increase over time, so that we don't blow up our regret over time, because that is what we're trying to minimize. So we say that we want to find sublinear rate of increase in the total regret over time. By sublinear, I just mean concave and not simply a sort of linear kind of rate of regret over time. So for example, I'll come to that later. Right. So that's what we're trying to do. This is the total regret. The next thing is that this is just a convenient mathematical characterization. NTA is nothing but the number of times we've chosen action A up till time t. So action A is just some particular action A. Remember, there are many different actions here, many different arms. And NT of A is simply the number of times that you have chosen action A, or the number of times that you pulled a particular arm or the banded up till time t. And obviously this varies over time as you keep, experimenting more and more with action A, then NT of A increases and so on. And capital delta A is just the gap between the expected value of the reward under the optimal action, or just regret basically, and under action A, which is this object. So it turns out, and this is convenient, that you can write the regret, you can equivalently express the regret in this way, where you just count the number of times that you have chosen any action A, and you do this for all actions across the set of possible actions. You just count NT of A up till time t. So regret at time t is equal to the number of times that you've chosen action A at time t, the expected value of that, times delta A, where delta A is just the regret from choosing action A. And if you think a bit about it, the total regret is just equal to the number of times you chose that action times its regret, right? So it makes a lot of sense. If you do this across all actions, then you'll just get the total regret, right? So it makes a lot of sense. So in this case, we just express the total regret as a function of gaps and counts. So this is the count and this is the gap. But obviously the problem is that these gaps are not known to us, because these gaps sort of depend on V star, and V star is not, we don't know what V star is because it depends on A star. If we knew what V star was, we wouldn't have this lecture. So what we do is that, well, there are various approaches, and that's what this lecture is about. One way is to sort of estimate, obviously if you don't know something, we try to estimate it using a sample analog. So Q of A is what is not known to us, right? So we can estimate it using Monte Carlo evaluation. What's Monte Carlo evaluation? Is just the average reward that you get in the sample up to time t. So for example, at time, this should be capital T. So up till capital time t, if you've chosen, whenever you chose the action A for a particular action A, of course, over time, you may not be always choosing this particular action A, in which case, I hope you know what an indicator variable is. I'm talking to the master's students. And this is just an indicator variable, which just takes a value of equal to 1 when it's just a dummy variable. When the event that AT is equal to A is true, and over time, since T is varying, if you choose something else and not the action A, some other action, then this will be just equal to 0. And obviously you don't get any reward from action A in that case because you never chose that. But over time, you just sum up this sort of indicator variable times the reward that you get at time t, which is what you observe. So remember, you do observe the reward over time as you keep on interacting with the environment. You choose an action, just like you pull a lever in the casino, you observe the reward immediately. So you know what the reward is after you've taken the action from that action. So the reward is a function of the action. And so you keep on adding the reward times this indicator variable, and then you just take the average. And obviously the average has to be with respect to NT of A, because that is the number of times that you've chosen this action so far. So this is nothing but the average reward that you've got from choosing arm A or action A up till time t, right? So this is why I have a Q bar over here, or in other words, this is just the sample analog or the Monte Carlo evaluation of the action value function, or the average, or this is the sample analog of the average of the action value function. So this is just Q bar, which is just the average reward they've got from action A up till time t. Yeah. So another thing that's sort of theoretically speaking, so I won't talk about this a lot, but I'll just talk about it intuitively. So remember, we're trying to discover A star, what is the optimal action over time, because you're trying to maximize the probability of reward. Or in other words, minimize total regret. And you'll minimize total regret if you choose an action A star as often, right? Because the regret will be 0 if you choose A star, because V star minus Q of A star is 0. So if the gaps in there are two things which make the bandit problem hard, or if these things are more likely to be true, then you have a harder bandit problem to solve, or it may take more time for it to solve and so on. But if the gaps in the rewards across arms are very large, then the regret will be larger as well, right? Then the trade-off or the exploitation trade-off is really binding, is really strong, because there's a lot of variation across the probability of rewards across these arms. If it is true that there's a lot of variation in the reward probabilities across the arms, then obviously if you explore something, you might get a really sort of really bad probability, and then you might get a very high probability also, but so the regrets are likely to be very large over time as well in expected value. If you have a lot of gaps in the rewards across the arms, and because we're not choosing the optimal action, you may be choosing the suboptimal action, which is going to give you a really low probability of reward relative to the optimal option. And another thing which makes these problems hard is that if conditional on some given size of the gaps across these rewards or reward probabilities, if the reward distributions are very hard to distinguish. Let's say all the reward distributions are normal distributions, all of them look very similar, they have only slightly different means. So it's very hard for us to distinguish these reward distributions corresponding to every action or every arm, right? And if it's very hard for us to do that, obviously it takes a lot of time for the algorithm to converge to the optimal action and to choose it with higher probability and so on. And these two things will make it very hard for us to solve the multi-arm bandit problem. I won't go into a lot of detail, but there's a theorem which says that one can sort of bound sort of below, or one can say that the total regret, remember LT, I already defined LT was just a total regret, expected regret. Asymptotically, as t goes to infinity, there is this theorem, which I won't prove, which tells you that the regret or the total regret asymptotically is at least logarithmic in the number of time steps. So you can't do better than this. So the objective, the reason why I bring this up is that we want to achieve logarithmic total regret. We don't want linear regret. We want the rate of increase of regret to slow down over time. So we want to achieve logarithmic regret. And this theoretical result guarantees that you can actually achieve at least logarithmic regret asymptotically, but you can't do better than this. So it is at least logarithmic, and it cannot be minimized beyond that. The rate of increase of the total regret is such that it is at least logarithmic in the number of time steps. So T is the number of time steps that you've carried out so far. And so log of T is so it's logarithmic in the time step. And then there is this other term which also shows up, which I'll come to. So delta A is, remember I said, the gaps. So the summation is just conditional on a positive gap, because obviously if you have a zero gap, then you just have zero. That's not important. So this term is proportional to the gaps. So if you have a larger gap across these arms, then this sort of log of T times this whole number becomes larger, right? So then the minimum bound of the regret is higher, which means that you're actually worse off, right? Because you cannot, because this is the minimum bound. So you cannot go below this, and you want to minimize the regret. So obviously if delta A is very large across all these, so the gaps are larger, then this term is going to be higher. So basically if you have large gaps, it makes it harder for you to minimize your regret because the lower bound is sort of very high now. Similarly, you have this another term in the denominator, which is basically known as a Kullback-Leibler divergence, or the relative entropy measure. If you don't want to go into technical detail, this is just some measure of the distance between two distributions. So just as we have the Euclidean distance to measure the distance between two real numbers, just as we have other kind of metric spaces, for those of you who know about real analysis, which can sort of measure distances between two functions over some domain, you have this various measures which try to quantify the distance or the divergence of the difference between two distributions, which is obviously a more complicated kind of random object. So it turns out that a Kullback-Leibler divergence, which is used a lot in economics nowadays, is also known as a relative entropy between any two distributions, probability distributions, whether they are continuous or discrete, doesn't matter. F and G this is just notation. D is for distance, KL is for Kullback-Leibler, and F, and these two bars are just showing that you're taking the difference between F and G. It's nothing but the expected value of the log of the ratio of these two densities, of the densities of those distributions, but the expectation has to be taken with respect to the first density F. So because you're measuring distance relative to F. This is just a formula for now. I don't want to go into this detail, but basically the idea is that there is this term in the denominator which is quantifying some sort of difference as you move over time. Remember, you're summing over A. As you move over time, you sum over A, you look at the Kullback-Leibler measure of divergence between the distribution of A, the reward distribution RA for A, and A star, which is your optimal action. And remember, if these distributions are very far apart, then your problem actually becomes easier because they're very easy to distinguish then, right? So if DKL is very high, so that the distributions are very different, and this is quantifying that, then obviously this term is going to be very small. And if it's very small, then you can actually, the lower bound of the regret is really low asymptotically. And similarly, if the distributions are very similar, then this distance is going to be very small, and this ratio is going to be very large. And so the minimum bound is really high. So you have a problem because then you cannot minimize it beyond that point. So the reason why I mentioned this is because this theoretical result allows us some sort of guarantee that it's possible to at least be logarithmic, to get logarithmic in the number of time steps, and that's our objective. So there are some algorithms, which I'll come to, which are called greedy algorithms, which can only achieve a linear rate of regret. And then there are other algorithms, which are more widely used because they're more successful, which is what we'll focus on, which are known as Thompson sampling and upper confidence bound algorithms. They can achieve the logarithmic sort of regret. And that is what we're after. Because this theoretical result allows us the guarantee that you can do this. You can achieve at least logarithmic regret, but you cannot do better than this. You cannot even go like become sub-logarithmic and so on. So for example, if you have sort of, this is called sublinear regret, because if you draw a linear line, it's going to obviously be steeper, and these concave functions are sublinear because they lie below the linear line for a large horizon T. And you can ignore these legends, but this is just from a computer science paper, this graph. And for basically, if the regret looks like this, on the y-axis you have total regret, and on the x-axis you have horizon. If the total regret has this sort of concave kind of sublinear kind of rate of increase, then this is what we want. This is what we're after. So basically, we're trying to look at different algorithms to help us solve this problem. So the most sort of trivial sort of approach, the most sort of natural starting point could be to just use what is known as a greedy algorithm. This is a very naive way to go about it, and it just doesn't work that well. And this has a linear rate of regret, and it has other suboptimal properties. So nobody ever uses this, but it's sort of, this is the most sort of, the first thing that comes in your mind. So remember, I defined this sort of Monte Carlo evaluation, or simply the average rewards that you're getting from action A up till time T, and you could do this for all actions. Over time, you could just, you observe the rewards for, as you keep on taking actions. So you could take an average across for each action of the rewards that you've got from that action up till time T. So the greedy algorithm says, so you simply maximize this thing. The way that you choose these actions over time, remember the objective is to choose an action profile or a policy over time. What do you do at each time? How do you choose these arms over time? That is the objective of the algorithm. So the greedy algorithm says that you should just simply look at the highest average reward that you've got so far, which makes a lot of intuitive sense, right? Because so far, based on what you've observed, you should just choose the action which has been giving you the highest average reward so far, right? And you should just do this all the time. At any time T, you know what these Monte Carlo evaluations are, and you know which action gives you the highest average reward. You simply choose it, and you do this for all time T. So it just chooses the arm which has the highest average reward up till time T. That is what the greedy algorithm is. The reason why it's called a greedy algorithm is that it maximizes sort of exploitation, but it sort of minimizes exploration. Because you're saying, well, so far I know that the highest average reward is coming from this arm, so I'm going to keep investing in this arm. I'm not going to try other things, right? So you're not exploring, but you're sort of exploiting to the fullest possible extent. But this is not optimal because you're not learning anything about the environment, right? So the reason why this is the machine learning algorithm is that through these kind of algorithms, our system is learning about the optimal action over time. But if you do this kind of greedy algorithm, then you can also link this to sort of regularization. you can think that, you know, the penalty parameter, which we discussed yesterday, lambda is sort of very low in this case. So you're not allowing the, a lot of exploration. You're just exploiting. Now, the problem is that, you know, if you have, this is sort of a probabilistic thing, right? So if you, let's say, if you interact with the environment the first 3 times, and the first 3 times you choose, you know, there are only 2 arms, let's say, and you choose the right arm 2 times and the left arm 2 times. And you were just lucky that the right arm gave you both successes and the left arm just gave you a failure. So the highest average reward is going to be of the right arm. So the greedy algorithm will say that at time 4, you should choose the right arm. And so on. So there's a possibility that you could get locked into a suboptimal action forever. And that's not, because it may be that the left action is actually sort of optimal, but just because you had a few unlucky trials and you're not exploring that other arm anymore because of the greedy, because you're very greedy, and this greedy algorithm doesn't do this well, and because it can lock into a suboptimal action, it doesn't explore enough, and it has a linear total regret. So the regret looks something like this. So some kind of linear thing over time for the greedy algorithm. The second algorithm is called the optimistic greedy algorithm. This actually does quite well in many applications, even though this also is not optimal and doesn't give you, but it's easy to use, and many applications it's actually not that bad. And yeah, you can use it in many simple applications, but this also has a linear rate of total regret, but it's better than the simple greedy algorithm. So what the optimistic greedy algorithm does is that it simply initializes all the arms at the maximum possible reward. So you know the set of possible rewards, and the optimistic greedy algorithm is we say that we're optimistic in the face of uncertainty. There's uncertainty because we don't know the reward probabilities. What we say is that we initialize all the all the arms that we have, and the average reward to R max, where R max is the maximum possible reward that you could get. And you say that so far, so I'm going to choose all of them equally likely, right? Because all of them are giving the same average reward. So I'm sort of being very wide in my exploration possibilities and so on. And so this encourages a lot of exploration. But again, you could also have a few unlucky samples, which could really convince you that, you know, Q bar was initialized, remember, at R max, but over time, as you keep on observing the rewards, you'll adjust this downwards. This can only be adjusted downwards because it cannot go above this. So you adjust these this average reward downwards as you keep on observing bad samples. But again, there's a problem here, because if you observe a few unlucky samples, you could again lock into an suboptimal action, or lock out of an optimal action forever. But this works pretty well in practice in many simple applications. The next algorithm, I won't go into a lot of detail for this, is called the epsilon greedy algorithm. So this is basically saying that with a very small probability epsilon, you have epsilon is a small number, but the probability 1 minus epsilon, you just implement the greedy algorithm, not optimistic greedy, the simple greedy algorithm, which just chooses the action which is giving you the highest average reward up to this time, right? With a very high probability, because epsilon is a small number. But with probability epsilon, you select some random action. You just randomize. So if there are k arms, with probability 1 over k, you select each one of those. So you're just randomizing with a very small probability. And this sort of, so you're exploring, this guards against sort of over exploitation. So allows you with some small probability of exploring even arms which have been fared not so well so far, but they may actually be optimal arms. But again, this also has a linear total regret. And this kind of, for the epsilon greedy algorithm as well as the optimistic greedy. And you have this kind of regret over time, which is sort of linear. So now I come to the upper confidence bound algorithm, and next the Thompson sampling. These two algorithms are widely used. The ones that I've discussed so far were just simpler. So it was sort of important to get you thinking about, what are the problems with some of the more commonsensical algorithms? Why don't they work so well? Because some of them are exploiting too much and exploring too little, and so on. And the random algorithm, the epsilon greedy algorithm, is randomizing and exploring to some extent, but sort of it's not finding any systematic or sort of optimal way to explore. So it also doesn't work well. So next I'll discuss the upper confidence bound algorithm, and after that the Thompson sampling algorithm. And these two algorithms are the most commonly used ones, and they work really well, and they do achieve the sublinear rates of regrets in many applications. Yes. So what we do with the upper confidence bound algorithm is that we construct sort of confidence intervals, just as economists are used to constructing them. You sort of construct 90, let's say 95% confidence interval. So any p-value that you want, 99%, 90%, depending on what sort of confidence you want in your results. And and depending on how you want to solve the exploration versus exploitation trade-off, you construct confidence intervals for QT of A, which is, remember, the expected value of the reward from an action A, which is what you don't know, right? And this is what you wanted to estimate using this sort of average reward from action A up to this point, which is Q bar, right? And this is what the greedy algorithm was maximizing, right? Q bar. So you have the same thing, which is a Monte Carlo evaluation, or in simple words, just the average reward from action A up to point T. You have this same term showing up, and then you add this sort of bonus for exploration, because you want to encourage exploration. Because remember, this sort of simple greedy algorithm doesn't explore much, and it only exploits, right? So it's exploiting too much and exploring too little. So the upper confidence bound algorithm says that you take this sort of Monte Carlo average reward from action A up till point T, and you add to it this bonus for exploration, this sort of surplus for exploration, which is the term U. And this is actually the upper confidence bound interval. And we'll construct a confidence interval, which will tell us that with the probability 95%, QT is going to be bounded below QT bar plus UTA. It's not going to go above this. It's bounded above by this with probability 95%. With 5% probability, it could be above that. But we can never know things with 100% probability. So now notice that, remember, NT of A was nothing but the number of times that you tried action A up till this point, right? So lower NTA means there's higher uncertainty, right? Because if you only explored an action a very few times so far, 1 or 2 times, let's say, then there's a lot of uncertainty because you haven't learned much about the distribution so far, right? And similarly, if you have high NT, then you'll have a lot of confidence because you've drawn more and more samples, you've tried action A more and more times, and now you're sort of pretty confident that the restaurant that you've been trying is actually a bad restaurant. And it's not that, you were just unlucky to get bad food the first time around. If you tried it 5 times, the food was bad all the time, then you can be pretty sure with a very high confidence that this is a bad restaurant. So in that case, UTA will become lower. So whatever Q bar is, which is your average reward so far, is going to be with 95% confidence, the actual Q is going to be pretty much close to Q bar plus some very small number. It's going to be less than equal to Q bar plus some very small number. So that is essentially equal to Q bar with very high probability if UTA is low. And UTA is going to be low when you've tried this action a lot of times. Similarly, if NTA is low, so that you've tried action A very few times so far, then UTA will be very high, so that whatever your average reward is so far is not very informative, and you have very large, this exploration bonus is very large and so on. So what the upper confidence bound algorithm does is, first it constructs this we will define this UTA in a moment. It first constructs this UTA thing, which is the upper confidence bound. And I'll come to how we construct this and how we define this mathematically. And once we've done that, it simply chooses, it's essentially the same thing as greedy algorithm, because if UTA were 0, you just have the greedy algorithm, right? It chooses the action which maximizes the average reward from action A across action A till time T plus this bonus term. So you maximize not Q bar, but Q bar plus U, where U is this upper confidence term. Or in other words, if you put it rather simply, you choose the action which has the highest upper confidence bound, right? So remember, again, you're being actually very optimistic in the face of uncertainty. So if you look at this diagram, so what the upper confidence bound says that, let's say there are 3 actions. So the green distribution and the red distribution and the blue distribution are 3 reward distributions for the action value functions. And there are 3 possible arms, and these are the distributions you have so far. So, and let's say that if you can see this sort of, these sort of dotted lines for the blue as well as the red distribution as well as the green distribution, these are the 95% sort of confidence intervals, or the area to the right of that has a probability of, well, you can say 5%, yeah. Well, it's actually one-sided interval, but yeah. So yeah, so it's not a two-sided interval as you're used to in standard econometrics. So the area of whatever is to the right of the shaded green line as well as shaded red line and blue line is 5% probability. So the upper confidence bound algorithm says that you should choose the blue arm because it has the highest 95% upper bound, right? Because blue is at 3.6, if you can see, which is greater than 2.9 as well as 3.3. So you choose, you're being optimistic in the face of uncertainty. Even though, the green, as you can see, the variance of the green distribution is very low, right? And the blue distribution has very high variance. It's all over the place. So you're very uncertain because you've tried the action A, or action which corresponds to action A1 actually, which corresponds to the blue distribution very few times. So that U is very large and a lot of uncertainty. So the variance is very large. And then on the other hand, green is something that you've tried a lot of times. So you have a very high amount of certainty that the expected reward is somewhere along this sort of, longer green line, which is the mean of the distribution. But since you're being optimistic in the face of uncertainty because you want to encourage exploration, if you are focusing on the greedy algorithm, you would just keep on choosing green over time, right? And if you would never learn whether actually blue is better than green, because so far you've tried blue so few times that you don't know. And so this upper confidence bound algorithm encourages exploration relative to the greedy algorithm by actually choosing the blue, the blue distribution or the blue action A1, because that has the highest optimal upper confidence bound. Now, of course, as you keep on trying blue, it may be that you get draws from this part of the probabilities from this part of the input space. So you keep on narrowing down this blue distribution. It may converge to somewhere over here. It may be that the expected value is just 0 with a very high, very low variance. So, of course, then you will stop. This will stop being the distribution of the highest possible upper confidence bound. But until you don't have that kind of uncertainty. As long as you are uncertain, you should keep on being optimistic in the face of uncertainty. And that is what the upper confidence bound algorithm does. So you maximize not Q bar, but Q bar plus U. You pick the action with the highest upper confidence bound. Larger UA is good for exploration, and smaller UA is good for exploitation. Because remember, if you choose a smaller UA, you should choose green. Green is good for exploitation because you know that with a pretty high probability, you'll get like a 2.5 kind of expected reward. And you're very certain about that. But then the red as well as the blue distributions could turn out with a very relatively non-trivial probability to be better than 2.5 on average, because so far there's a lot of uncertainty. So the upper confidence bound encourages exploration by narrowing down the uncertainty regarding the distributions which you haven't explored so far. So that's it. Then there's this. This is just standard result and probability inequalities. So if you have independent identically disputed variables in the unit interval from x1 all the way to xt, and we define the average of these random variables as x bar capital T, then this is just an inequality, which I won't have time to discuss in detail, but this is just some theoretical result which we're using from probability theory, that the probability that the expected value of x, which is what we don't know, is greater or it deviates from the mean that you have so far by a magnitude of greater than u. Or if you just rearrange this is telling you the probability that the expected value of x minus x bar t, which is the mean that you have of these random variables so far, which is the empirical mean, is greater than u, or the probability that your empirical mean deviates from the true mean basically is bounded above, so that it's not greater than that, because you want to bound this probability, right? Because you don't want your your empirical information to be a very bad approximation to the true mean, right? You want to learn, because in statistics the whole point is that you don't observe the population and you want to infer based on the sample. So you want the sample to be informative, so you want to bound this probability above, and it turns out that the Hoff-Dings inequality bounds above by an exponential term, which is quadratic, not quadratic, but exponential. That exponential term is quadratic in u, which is the difference between the mean and the population mean and the empirical mean. and then capital T is the number of time steps so far. So the reason why I mentioned this is that you use the Hofding's inequality to choose an upper bound, which is equal to P. Let's say you want to choose a value of P equal to 0.05. That will correspond to a 5% probability to the right of the upper confidence bound, or 95% one-sided upper confidence interval. And because remember, we want to define the term UTA, because if you don't know what UTA is, we can't solve this problem. We know what Q bar is. This is just an average for each action of the rewards. We don't know what UTA is. So we want to define what UTA is. For that, we want to use the Hofding's inequality. And once we've used that, we just equate the upper bound, which is this exponential term, from the Hofding's inequality with P, which is the level of significance that you want to achieve, let's say 0.05. And then we just solve this and take logs on both sides, and you just get a sort of clean sort of expression for the upper bound, which is logarithmic inside the quadratic term in the probability P, and NT of A is the number of counts that you have. So notice that this is not a negative square root. Log of P is negative because P is a number between 0 and 1. So negative of log P is positive. So there's no problem here. So log of P is negative because P is the number between 0 and 1. Right. So we want the probability P to decay with capital T, right? Because if capital T, remember, is the number of samples you've taken so far. So as you keep on interacting with the bandit over time, you want your information to be pretty precise, right? So you want this upper bound to be pretty binding or pretty sort of tight, because you want to learn more and more about the true mean based on over time, right? You want information to accumulate over time because you want to learn more over time. So you want this sort of the value of P to decay over time. You don't want it to be constant. So I just gave an example that P could be 0.05, but if you could actually say that I want P to decay over time. So for example, we could choose P equals C to the power minus alpha, where alpha measures the degree of decay. And so in this case, your confidence will increase over time, and the upper bound will become tighter and tighter over time. And yeah, so if you use this, and it turns out, I'm not going to go to the details, but if you use this P equals C to the power minus alpha to decay the probability and make your information accumulate more and more over time, then this is the expression that you get in terms of alpha times log of T for the upper confidence bound, which is logarithmic inside the square root in the number of steps so far, capital T. NT of A, remember, for action A is the number of times you've chosen that action so far. So it makes sense, right? As I said, if NT is high, then you should be more confident and UTA should be low. This is exactly what happens. If NTA is high, then UTA is low, and vice versa. Similarly, if log of T is high, then UTA is high, and so on. And once you just substitute for what you've, this is the mathematical formulation of the problem that a UCB algorithm is solving. And this algorithm, unlike the greedy algorithms, does have a logarithmic sort of asymptotic total regret. Yeah. And the next sort of, yeah. So it has this kind of, UCB algorithms have these kind of, you have these kind of asymptotic sublinear regrets, which is what we're after. The last sort of, which is sort of more important, because both applications, economic applications that I have, yes, both economic applications, no, well, at least a major one, which I'll focus more time on, actually makes use of Thompson sampling and not the UCB algorithm, but both of them are widely used to solve multi-arm bandit problems. But the paper that I really liked, which is what I said was a working paper, which was going to be published next year, I think, it's not published so far, makes use of Thompson sampling, and that's sort of more commonly used. Because, yeah, Thompson sampling is the only algorithm which achieves asymptotic, which achieves sort of logarithmic or sublinear regret even in finite samples. So it has a better performance relative to even UCB algorithms in many settings. Even though both of them achieve asymptotic sublinear regret, but in finite sample performance of Thompson sampling is better. So we've done UCB algorithm. Now the last category of algorithms that I'll cover before we move to applications is Thompson sampling. Now, Thompson sampling is just a sample analog of what is known as probability matching. So it's essentially probability matching, but the sample analog of that, because probability matching is not feasible because it requires information that we don't know. So what is probability matching? It's actually, it's very simple. All it says is that, so just to clarify, this curly H is referring to history of information that you have so far over time. So this curly T or capital T is the time horizon that you have been exploring so far. So if you've played with the bandit for 10 periods so far, T will be 10. And remember, there are two things that you're observing here, right? Because one is the actions, because you know what action you took at time A1, A2, A3, and so on, right? You know the entire history of actions that you've taken so far. A1, for example, could be that I chose the first bandit. A2 could be that arm of the bandit, or A2 could be I chose some other arm, and so on. And so I know this history of actions. I also know the history of rewards. So when I chose action A1, I observed reward R1. When I chose action A2, I observed reward R2, and so on. And so I know both of these things. So R to the power T means history of rewards. A to the power T means history of actions. And both of these things are part of this history. This includes the history of rewards as well as history of actions. And so basically probability matching takes a Bayesian approach. So upper confidence bound takes a frequentist approach, right? It simply looks at the Monte Carlo empirical mean and then bounces upwards. There's no Bayesian updating. But probability matching takes a Bayesian approach to this problem, and the same is true for Thompson sampling. So what you do is that condition on the information set that you have at time t, and this evolves over time, obviously, because the information is accumulating and expanding over time as you take more actions and observe more rewards. You learn more about the reward distributions. So conditional on information at time t, the probability matching approach to the multi-arm bandit problem says that the probability with which you want to choose action A. So here you actually mix. So unlike the greedy algorithm and unlike the upper confidence bound algorithm, which simply chooses one action, remember, it says you choose just one action which has a maximum upper confidence bound. Similarly, the greedy algorithm says there's no mixing. You just choose one action which is giving you the highest average reward so far. But this sort of Bayesian approach tells you the probabilities with which you should choose these different actions. So for example, if pi of A is 70%, pi of A is just the probability with which you should, or rather the frequency with which you should choose the action A conditional on the information so far. Is 70%, you choose it 70% of the time, and 30% of the time you may choose all the other actions. And this probability is defined for all the actions. So you know that the probability for the other actions as well. So you know all these probabilities, they all sum to 1, obviously, across the actions, and you know the relative frequencies with which you should choose all these actions. So it just says that you should choose the probability with which you should choose the action should be proportional to the probability that this is the best action condition on your information. So the posterior probability after the Bayesian updating has been done, after the observation of rewards and the accumulation of this history, whatever the posterior probability condition on this information is, that this action A, a particular action A, is the best policy or the best is the best action, is the probability with which you should choose the action. Makes a lot of sense, right? So probability with which you should choose action should be equal to the posterior probability based on Bayesian updating that this is the best action. So it makes a lot of sense, very intuitive. This second is this is just I don't have time for this. It's just the same thing. It's just that the probability that Q of A is better than all other Q of A prime, which just means that this can be equivalently expressed as the fact that A is the maximum across Q of A. But since this is the probability, it turns out that this is the basic fact from probability theory that if you're calculating a probability of any event, you can equivalently express it as, and if the event is that Q of A in this case is the best action, so that Q of A gives you the highest average reward relative to Q of A prime for all A prime not equal to A. For all other actions, Q of A gives you the highest reward probability, highest average reward, right? So if you have this kind of probability, it turns out you can always write it equivalently as the expected value of an indicator variable, because the indicator variable is just a 1-0 variable, and the expected value of an indicator variable just gives you the probability that this event is true, which is that the action A is the best. So all this means is that you choose action A with respect to the probability that this is the best action, conditional on your information. That's it. And again, this is also trying to encourage exploration and optimism in the face of uncertainty, because more uncertain actions or arms will have higher probability of being the optimal action, because there's a lot of probability mass because of the uncertainty, which is associated with very high average reward values as well. So this probability that action A is the best action will be very high for those actions which you haven't explored so far a lot. So again, this is also just like the UCB algorithm is encouraging exploration. But the problem is that you don't know this, right? If you knew what the probability, analytical computation of this posterior is very hard. So because these posteriors have, in many cases, don't even have analytical expressions. And if you don't have conjugate priors, then the distribution may not even be constant over time. So it's very hard to sort of find an analytical sort of closed form solution, unlike the UCB algorithm, in which you had an analytical solution for the upper confidence bound. This is not feasible. You cannot, in many cases, analytical or closed form computation of the posterior is not possible. So this is probability matching. And so we use Thompson sampling, which is just the same thing as probability matching, but it just, rather than taking the population expectation, it approximates the sample version of that. It just takes based on your information so far, it updates in a Bayesian manner, and it estimates this population expectation, which is very hard for you to compute. So its probability is the sample version of population matching. That is what Thompson sampling is. So what it does is that it takes a Bayesian approach. So you choose a prior distribution over theta. Theta, remember, are reward probabilities. Theta 1, theta 2, theta 2k, I said in the beginning, were reward probabilities, the probability with which all of these arms are giving you a reward versus no reward. And so you choose some sort of prior distribution because you're taking a Bayesian approach over these parameters theta, which govern the distribution of outcomes across these arms. And then the hyperparameters, which I hope that people know about Bayesian. So the parameters of this prior distribution are known as, so theta itself is a parameter, which is the probability of success. But theta is not a hyperparameter, it's just a parameter. But when you're choosing distributions for some prior distributions for parameters, and of course, those distributions in turn will also be defined by some new parameters. And those parameters are called hyperparameters. And they are updated over time in a Bayesian manner using Bayes' rule in Thompson sampling, which takes a Bayesian approach. And as you keep on updating these hyperparameters over time, and as the hyperparameters change, obviously your estimate of the distribution of theta is changing, right? Because the distribution of theta is pinned down by, theta itself is a parameter, and the distribution of theta is pinned down some other hyperparameters. And as you keep on updating those hyperparameters over time, you keep on updating your information about these reward probabilities, and you keep on allocating to arms which have the highest reward probability. And that's what you do in Thompson sampling. So you choose a prior distribution for Q of A as well as theta. So let's say we're just dealing with the Bernoulli context, which is the simplest example. So you just have a probability of either a success or a failure for each of these K arms. So theta, the prior distribution for theta is a Bernoulli distribution. But it turns out that when you have a Bernoulli distribution for theta, when you have Bernoulli trials, the average sort of reward has a beta distribution, which is what we're interested in. And the beta distribution has two parameters, alpha and beta. These are known as shape parameters of the beta distribution. And the reason why we're using this is because it's very convenient. If you have Bernoulli trials, we know that beta distribution is a natural choice because beta distribution always lies in between 0 and 1. And for Bernoulli trials, the average reward will always obviously lie between 0 and 1, and so on. And another really neat thing about beta distributions is that it's very easy to update these hyperparameters. Alpha and beta are known as hyperparameters. It's very easy to update them over time because they have a very natural interpretation in our context. alpha is simply the number of successes that you have for any action A. So for each action A, you have this distribution. And yeah. So alpha Ti just means the number of successes that you have up till time T for action I. And beta Ti, I should actually have used A here, but is simply the number of failures that you have for action I up till time T. So it's very easy to update the beta distribution over time by simply observing the number of successes and failures as you keep on pulling these arms in the bandit and updating the beta distribution accordingly. And once you've done that, the Thompson sampling algorithm basically samples from this posterior distribution in a sort of Monte Carlo Markov chain, MCMC type of algorithm. But basically, you have the posterior distribution, which in this case is going to be a beta distribution. You sample from the posterior distribution an expected reward Q hat. I say Q hat because this is not a true Q, but a sample from the posterior distribution of Q conditional on time T information history. And then once you've sampled these rewards, expected rewards from all these distributions for all the actions, the Thompson sampling decision is that at time T+1, you should simply choose the action which gives you the highest expected reward based on the sampling that you, this is why it's called Thompson sampling, because it samples from the posterior distribution. And once it has sampled these expected rewards, it simply chooses the best action which gives you the highest expected reward. So for example, in the Bernoulli case, the reward could either be 1 or 0, right? It's just 1 or 0. So when you observe a true reward, this is how you update these parameters. Initially, you had this hyperparameter at time T, and at time T+1, you take any action AI. I should just call it A, but AI means it's a particular action. So you have to take a certain action AI at time T based on your previous Thompson sampling decision. And when you take that decision, you observe whether you get a reward or not, right? So if you took this decision, this indicator variable will be equal to 1 times RT, which will be equal to 1 if you get a reward. If you didn't get a reward, then R will be 0. You don't add anything because remember alpha is a number of successes. So obviously the number of successes will be simply equal to the number of successes in the last period plus 0. Like if you have no new number of successes. But if you did have a success, and RT will be 1 when you tried the action AI. So this whole term will be 1. So you'll add 1 in the number of successes. And similarly, beta measures the number of failures. So if R was 1, so that you actually got a success, then obviously this term will be 1 minus 1, 0. And then you add nothing to the number of failures and so on. So in the next period, the beta distribution will now have these new updated hyperparameters. And you sample from this. And once you've sampled this for each action A, and then you choose this way, the action which gives you the highest expected reward from the posterior distribution based on the sampling from the posterior distribution. Yes, from the beta distribution in this case. So I come back to this sort of octopus diagram because these sort of green distributions are basically beta distributions. So you choose, in this case, actually, it's not very clear in the diagram, but actually you should choose E. So if you can see that if you sample from the E distribution, you have this vertical line, which will give you the highest expected reward from the sample. If you sample from this beta distribution, all of these are beta distributions with different hyperparameters. Because remember, there's one hyperparameter for each I, and I is referring to the action. So there is a hyperparameter for each action I. So there's an array of beta distributions. There's not one beta distribution, one for each arm. And you're updating all of these simultaneously over time as you keep interacting with this environment. And so in this case, you should choose arm E. The octopus should choose arm E because that has the highest expected reward based on a sampling from this beta distribution. And obviously, as you keep sampling, alpha and beta hyperparameters are updated over time. And the beta distribution, obviously, all these beta distributions will change over time. So I have this cool graph here. So for example, the beta distributions will keep on changing over time when alpha and beta are changing. So if alpha is really high relative to beta, you have, you saw just now, or similarly in this case, alpha is really low relative to beta. In this case, when you're towards the left. And if you're skewed towards the right, you can see alpha was something 0 something and beta was very high. In the opposite case, alpha was 5 and beta is 0 point something. So if you're skewed towards the right, alpha is very high and beta is very low. And alpha, remember, is the number of successes. So if the number of successes so far are very large, and as they keep on growing, you become more and more right skewed, and they're more and more likely to choose this arm with a higher and higher probability. So this is just a simulation of the beta distribution as I vary the shape parameters. So this is a very flexible, sort of beautiful general distribution which changes as a function of these hyperparameters. And yeah, so the Thompson sampling algorithm achieves the theoretical lower bound, which we discussed, which was logarithmic in the number of steps. And yeah, and for Bernoulli bandits, it achieves this in sample or with a very high probability, with a very high precision, even in a relatively small sample for Bernoulli bandits, especially, and works very well in practice for Bernoulli bandits. The last topic is sort of more relevant from an economic perspective, because this is very brief. I only have one slide on this. So this is just an extension of the standard bandit problem. This is known as contextual bandits. So far we had non-contextual or acontextual bandits, in which we only had information about, remember, the rewards that you observe as a result of each action that you take. You don't observe any individual characteristics, because so far I was just telling you about, the arms of a casino bandit. But in practice, these arms are actually individual people. In economic applications, these arms are not the arms of a casino, but they are either people or they're either prizes which you want to target or experiment with. So we want to allocate people to different treatment versus control groups. And yeah, sorry, the arms are not people, the arms are the treatments, but the people are the units which you have to assign, data points which are coming over time to any one of the treatments. So typically you will have data on these people, right? You will have data regarding their age, their gender, their demographic, and other economic information, labor market, search history, whatever. So typically you'll have data on xi, or which we call attributes in the machine learning literature, or features. In economics, we call them explanatory variables or conditioning variables. So if you have those variables, then bandits sort of become sort of hierarchical, multidimensional, and really a bit complicated. Then you'll have to use sort of what are known as, well, one approach is to use a hierarchical Bayes models, which I don't have time for. But basically, the basic point is that previously we were just, y here is the outcome, which could be 1 or 0, or the reward. And D is the treatment. Yeah, so this is different notation, but D is the treatment, Y is the outcome, which could be 1 or 0, X is the covariates, such as age, gender, and so on. So in this case, the distribution of the outcome, Y, is not just, previously it was only conditional on the treatment. Remember, previously the reward distributions are dependent on A. Here R is Y and A is D. Sorry for the change in notation. And here the reward distribution Y is no longer just conditional on D, which is the treatment, which was previously A, or the arms, but it's also conditional on X. So it's conditional on two things, because whether you end up getting a certain outcome as a result of an experiment will depend not just on which treatment you're allocating this person to, but what kind of person he is, right? Because if you're allocating really elderly people to certain kind of, or gender differences, all kinds of things, to a different drug test, you'll get different results based on individual characteristics. And the outcome or the treatment assignment will depend not just on which treatment you've assigned to. So there's variation across treatments, because some treatments are better than others, right? Some drugs are better than others. Some economic interventions and RCTs are better than others. But it's also that the effect of these interventions varies by individual characteristics. So in this case, the distribution of Y has to be chosen conditional on not just the treatments D, but also, or the decisions D rather. Treatments are also decisions, so that's why the word D is used, and X is the covariance. So it has to be, you have to choose some distribution F, which is conditional on both of these things. And you have to update the parameter theta, which is the probability of success in each one of these treatments. Remember, we had theta 1 all the way to theta k. You have to estimate that as a function of not just treatments. Previously, we had 1 theta for each treatment, but now we have 1 theta for each treatment. Not just that, but we have D times X number of T times number of X variables that you have, number of coefficients, because the coefficients vary not just across T, which are the treatments or the decisions regarding treatments, but also X. So yeah, so this becomes complicated because here you have to choose a model which maps not just the actions or the arms to the reward, but also you have to take account of the fact that different user characteristics have to be mapped to expected outcomes. So, and previously all the units were identical, right? So far, whatever units were coming in over time were identical. There's no difference between the units which are coming over time so far, right? But in contextual bandits, if you're dealing with the units are actually people, and of course they're not identical, they're different, and they don't share the same what we call the context, or you could think of it the same. They don't share the same characteristics which are relevant for the outcome variable of interest. So therefore, in that case, whatever you learn from experimenting with a certain individual that comes at time t by allocating him into a certain treatment group, whatever information you learn is going to be of some use, and it's going to help you learn not just the probability of success of this treatment, but also going to help you learn something about the mapping between characteristics and the outcome variable, and the extent to which whatever you've learned at time t is generalizable to time t+1 will now become limited, because what the individual which is coming to you for a treatment assignment time t+1 is a very different individual. He may have a different gender, he may be older, he may be smarter, and so on. So they have different xi, and this sort of complicates and adds sort of more layers of complexity in the bandit problem, and these are known as contextual bandits. So now I'll discuss one application, which is, I thought, really cool. This is sort of really interesting because, so far you might have thought that, we're constructing this we're sort of drawing from beta distributions, or even I thought that way, that, we're dealing with sort of a theoretical sort of Bayesian analysis of how you're updating information over time regarding reward probabilities. But in this case, actually apply this, which is very exciting and a source of a lot of, I think, a pride for people who develop these kind of algorithms. Amazing work by Cario et al. And other, and Simon Quinn at Oxford and Max Cassie at Oxford and other people from the International Refugee Foundation, which is still under progress. They use a version which they call the tempered Thompson sampling algorithm. Obviously, in this lecture, the point was to introduce the Thompson sampling algorithm. So and other algorithms, and I'm not going to talk about extensions, but of course, there are lots of extensions of Thompson sampling algorithms. So they have a slight extension of the Thompson sampling algorithm. They have a contextual bandit because they're dealing with people. And what they do is that they use these kind of algorithms to improve job finding rate for Syrian refugees in Jordan. So I thought it was really cool. So since it's sort of Syrian conflict, Jordan has received close to around 10% of its original population size as refugees, which is around 700,000, based on UNHCR Syrian refugees. Now, of course, and then there was this concern that because of legal restrictions, the refugees could not find work. But of course, that creates a lot of unrest because obviously unemployment leads to all kinds of problems regarding crime and, of course, human welfare considerations. And so there was this international compact, which was signed by Jordan in 2016, that in exchange for some kind of trade concessions from many Western European countries, they said that some conditional financing, which is going to help them deal with this refugee crisis, Jordan agreed that they were going to provide 200,000 work permits for refugees, and they're going to lift these sort of legal restrictions on work, on job search for refugees, so that they can work within Jordan and find work. Now, and the problem arises that how do you, but the problem is that despite this, the unemployment rate is quite high among these Syrian refugees, especially, but also low-income Jordanian indigenous people as well. So what this algorithm does is that it has their paper has a twofold objective. They're trying to, of course, measure, the treatment effect of various treatments, which is what we've focused so far, that we want to figure out these reward probabilities, right? And we want to maximize the reward by allocating to the reward. Yeah. But in this case, they're also interested in participant welfare. So they're using it for a sort of welfare objective as well. So they're trying to optimally allocate people over time to various treatments so that they can improve labor market outcomes for these Syrian refugees in Jordan, as well as for indigenous Jordan low-income people as well. So they have 4 interventions. So you could think of these as arms. So there are 4 arms of the bandit. So one is a cash grant. They give an unconditional cash grant to these refugees, roughly 3,000 odd people in their sample. They give a cash grant, not to all of them, but to those individuals which were assigned to this treatment of cash grant. They give a cash grant, unconditional cash grant, and then they look at labor market outcomes after 6 weeks, after 2 months, after 4 months, and so on. So here, sort of the labor market outcome that they observe is not literally immediate. In a sort of casino analogy, you had this immediate reward. Here they observe labor market outcomes obviously after 6 weeks. You cannot observe them immediately after the intervention. But basically 6 weeks is sort of the analog of the immediate reward, because in the middle, so the time t is going to be, time t and t plus 1 is going to measure in the units of 6 weeks, let's say, and so on. In fact, well, time t is the start of the experiment, t plus 1 is 6 weeks, t plus 2 is actually 2 months. They are uneven, and t plus 3 is 4 months, because that is the frequency after which they get new information. That is the time after which they get new information. And they update it through Bayesian analysis, and they do Thompson sampling. So they have 4 different treatments. They have a cash grant. They have a behavioral nudge in which they motivate people. They give people a calendar, and they give people training regarding how to find jobs and so on. Maybe training regarding other issues, cultural shock issues, and how to navigate a Jordanian labor market. And that is what they call a behavioral or psychological nudge or intervention. The third treatment is the information provision. They provide more information about job opportunities available, in their local community and so on. And the fourth treatment is just the control treatment. They don't do anything, and they observe these people over time. These are the 4 arms of the bandit. And traditionally, the sort of, if you were doing an RCT in this kind of experimental context, so you would just allocate a certain fixed predetermined probability, all of these treatment and control groups, right? But that is, a modern experimental allocation is more complicated than the traditional RCT design. And these people use multi-armed bandit problems to do more efficient experimentation. And this is sort of dynamic. So based on the information that they learn from whatever people they've assigned to a cash grant versus a behavioral nudge versus information provision, and they look at the effects of these experimental interventions in the field experiment on labor market outcomes. And based on that, they keep, updating their estimates of the probability of success, where this is also Bernoulli, where in this case, the success probability is the probability of finding a job, right? And the failure is the probability of not finding a job after 6 weeks, despite the intervention. And they learn over time based on whatever outcomes they've observed regarding these different treatments. And also they have data on individuals, like whether they are Syrians versus Jordanians, whether they are male versus female, ever employed versus never employed, age, and so on, income and so on, and other variables as well. The time since you've been a refugee, or all kinds of things can be thought about, family size, which could be relevant in this context, urban, rural, all kinds of things. Labor market tightness measures. If you're in a region within Jordan where the labor market is very tight, then you're likely to have a very low probability of finding a job, even conditional on this treatment. So I'm not sure if they have all of these control variables. I just came up with a few of them on my own. But yeah, I think a few of them, they probably don't have it, but I guess they should. Or maybe they do as extensions. So this is still ongoing work. So they have these interventions, and based on the outcomes that they observe regarding these interventions over time, they change the proportion in which they allocate people to all these 4 treatments. So for example, so this is very interesting if you think about it, because traditionally you just, let's say, allocate 25% of people to each group. But that's actually very inefficient if you're interested in maximizing participant welfare from this kind of intervention. Because, if the cash grant is working better, and if you've observed it, after the initial few months, or let's say few weeks, after 6 weeks, and then again after 2 months and so on, and you keep on observing that a cash grant is doing a lot better in terms of labor market outcomes. And you should allocate a higher proportion of people to cash grant, right? You shouldn't allocate 25% to all groups. You should allocate maybe 40% to cash grant. And these probabilities of allocation will be, remember, determined by the Thompson sampling algorithm, because the Thompson sampling tells you, the probabilities with which you should choose all of these actions. So they find a systematic way to allocate people to all these 4 treatments. And they find that after 4 months, the cash grant has a very sizable effect on the employment and earnings of Syrians, but other variables only have short-term effects. And the idea is that, it shows importance of sort of liquidity constraints and sort of hindering employment opportunities and job search intensities in developing country labor markets. So that is just economics. Now, those of you who are aware of RCTs and sort of the statistical power properties of the RCT experimental design might have wondered that the reason why, in RCTs, you're just assigning a 25% probability to all of these 4 groups is because you want to maximize the statistical power of the test that you're trying to conduct, where the test is actually the statistical significance analysis of the difference in the average treatment effect across these treatments. And if you're interested in a very precise estimate of the treatment effect for all of these 4 treatments, then you should assign a more or less equal proportion of people to all of these treatments, right? Otherwise, you would have very unbalanced sort of panels, samples across people. If you've only allocated, let's say, 500 people to one of these treatments, but all the other treatments have 1,000 each, and you have 3,500 people, then you're going to get a relatively imprecise estimate of the treatment effect or of this treatment effect, for which the sample size is only 500. And this is why in traditional sort of RCT, you assign treatment D to individual I with probability 1/k, where k is 4 in this case, simply 1/4. But what they do is they don't do this because they're trying to balance 2 objectives. They're not just interested in the precision of the treatment effect estimates, but also they're trying to maximize participant welfare. So there are 2 objectives here. So in traditional RCTs, there's no objective of trying to, there's no welfare objective. And this is why sort of Angus Deaton and other people have sort of criticized the sort of RCT literature, is that you're doing these experimental interventions such as, cash grants and so on, and trying to look at the impact on poverty and other labor market characteristics, but you're not actually trying to improve people's welfare. So it has no welfare consequences, because by design, you're just, randomizing across all these treatments. Some of them may be good for welfare, some of them may not be. And you're simply interested in measuring these sort of from a purely scientific perspective, the treatment effect of the various treatments, but you're not interested in trying to allocate people to treatments for which the welfare effects are stronger. So there is no sort of welfare or normative kind of goal behind these experiments in the standard RCT case. But in this paper, what they do is that they try to do something from a welfare perspective. They have welfare objectives as well as statistical objectives. Now, obviously, there's a trade-off, because if they use Thompson sampling too much, then the Thompson sampling may allocate, very strongly people towards those treatments which work very well. But the problem is that, and that may be the optimal treatment, but for all the other suboptimal treatments, because the Thompson sampling is good at discovering the optimal treatment, but for all the other treatments, you get a pretty bad, statistically, very noisy estimate of the treatment effect. And as sort of economists, as sort of people who are interested in statistical analysis and statistical sort of, we're trying to measure these treatment effects, and that's also a secondary objective that we have. We're not primarily, trying to do philanthropy, even though it's good to do that. So we're trying to balance this trade-off. So what they do is that with some probability gamma, which is actually a small number, so they are primarily focusing on welfare improvement, but with some probability 20%, where gamma is 20%, they essentially do RCT, the standard RCT, in which they allocate this individual I with some characteristics, xi, with probability 1/k to all the treatments, to any treatment D, where D is the treatment. But with higher probability, let's say 80% of gamma is 0.2, 1 minus gamma, they allocate the individual with the probability which is equal to p hat dx, where p hat dx is nothing but the probability that you get based on Thompson sampling, which is actually theta in our previous, But since, this is actually a more complicated bandit, because they also have data on contextual So I said that if you have contextual bandits, then your probability will depend not just on the treatment D, but also on the characteristics X, which is why, because the treatment effects vary across Syrians versus Jordanians, treatment effects vary across males versus females, and so on. And so therefore, this probability depends on both D and X. And you update these probabilities over time across treatments as well as across individual characteristics. And you optimally allocate based on this Thompson sampling probability. But you don't do, this is why they call it tempered Thompson sampling, because you've tempered the Thompson sampling algorithm. You've sort of tied its hands with a very small probability, 20%. You're relatively small. You're not doing Thompson sampling, but just doing RCT. If gamma was 0, you get standard Thompson sampling with contextual bandits. Gamma was 1, which is what we've covered. Gamma equals 1 will give you the conventional RCT with no Thompson sampling and no adaptive treatment assignment. So as I said, when you have contextual bandits, and the sort of things become a bit more complicated because there are various levels at which you have to think about things. The problem becomes sort of multi-layered, because now you not just have treatments D, but also X, which are the variables. So the outcome Y, which is the probability of finding a job in this example from this paper, for individual I at time T with for treatment D is conditional on the characteristics of that individual that you observe at time T, as well as, so you have this X term coming up, which is a new term because this is a contextual bandit. And we've not focused a lot on contextual bandit in this lecture, but this is a more complicated form of bandit in which we also have to keep track of individual characteristics. So the success probability of finding a job for treatment D, where treatments, remember, how the behavior nudge, the cash grant, the information intervention, and the control group in which you do nothing. So for treatment D, the probability of success for individual I at time T, it's conditional on, or it depends on, this is just a Bernoulli variable, but it's conditional on characteristics of the individual, because the probability of success can depend on the characteristic of the individual. More experienced individuals may be able to find jobs better and so on. And also depends on these hyperparameters, which govern the beta distribution. And they also depend on the theta, because the Bernoulli variable has a probability of success, which is equal to theta dx, where theta dx is just the probability of finding a job after 6 weeks, let's say, for treatment D and individual characteristics X, right? And then, so this is what is known as a hierarchical Bayes model. So it's slightly complicated. It's not that complicated, but now this sort of, in addition, because there's sort of multiple layers of complexity here, and this is what is known as a hierarchical Bayes model, hierarchical Bayesian model. So you have that the treatments depend on X and theta and these hyperparameters, because theta depends on these hyperparameters. But the theta, which is the probability of success, remember in the Bernoulli case, the probability of success has a beta distribution, right? It has a beta distribution with these hyperparameters alpha and beta, just as before. But now we have to also, just as before, but there's an additional step that these hyperparameters themselves have to be drawn from a prior distribution. So this makes things a bit complicated, but this is the model that they use, and then they apply so the Bayesian updating becomes more complicated because of this, but essentially they're just doing Thompson sampling and Bayesian updating and drawing from a posterior, which just has a very complicated form in this case. But theoretically, the idea is simple. It's just that in this case, the Bayesian updating has a very complicated analytical form, because you have all these distributions. And pi is called the hyperprior. Previously, we had no hyperprior, we just had hyperparameters. But in this case, these priors themselves are random objects, and they're being drawn from this posterior distribution over time. So I have the algorithm here, but you can read their paper. I don't have time to discuss, but they basically do a Markov chain Monte Carlo kind of algorithm and they have the details in their paper for the hierarchical Bayes model. And as they keep observing, more and more successes, which are probability of finding a job, as they keep observing that people found jobs in response to certain treatments, but not in response to other treatments, they observe the beta distribution over time by adding, rewards and adding failures to beta and alpha. Alpha and beta, remember, are success and failures. So they observe the beta distribution over time by adding the rewards, which is just a number of successes over time that they observe, and also adding M minus R, where this is just a number of failures. But then, you're observing this across both treatments as well as across individual characteristics. So that makes things sort of multi-layered and complicated and hierarchical. Apart from that, this idea is the same. So this is really cool. So this is a graph from their paper. So in the start of the so this is the assignment probability to each treatment. And there are 4 treatments here. The sort of dark, sort of purple one is the cash grant, unconditional cash intervention. The blue one is the information treatment, in which they give information about the labor market. The nudge is the sort of the green one is a psychological intervention, in which they're trying to motivate people to work harder to find a job in the labor market. And the yellow is the control, in which they do nothing. And obviously the effects are measured relative to the control. So, and this is the week of the experiment. So, and the start of, towards the start of the experiment, which was you had 0 weeks, you just had a 25% sort of prior probability, because you just had a sort of uniform kind of diffuse prior for all these assignment probabilities, theta. So relatively, this number is 25%, as you can see, is between 0.2 and 0.3. So all these, so the yellow line is actually on top of the green and the purple and so on, because all of these are lying on top of each other. This is 25% probability of allocating to all these treatments. So in an RCT, this number will stay constant over time. But in this sort of multi-arm banded problem, it's sort of over time, dynamically, they're adjusting the frequencies which you want to allocate people to different groups. And this also depends on characteristics also. Remember, so this is really cool because they're accounting for the variation across people, individual characteristics as well as the variation across the effectiveness, variation of effectiveness across the treatments. So there are 2 dimensions which are varying here, which is why they have to use a hierarchical Bayes model. And as you can see that over time, you want to, increase the frequency with which you're sort of, allocating the cash transfer. It increases almost to above 30%. The reason why this is not going even above that is, remember, this is a tempered Thompson sampling algorithm. This is not pure Thompson sampling, which is what we've covered in this lecture. So with some probably 20%, they were not doing Thompson sampling. They just randomly chose, because they were also interested in, otherwise you get very poor statistical power of a very poor precision of the treatment effects. So you have a 2-fold objective. You want to maximize welfare, but you also want to be scientific and measure the treatment effects very precisely. So otherwise this probably would have gone even above. So, and I don't know why this is happening. They don't discuss this in their paper, but they have this sort of shaded as Ramadan. So in this sort of holy month for these people, sort of you can see that this, I don't know why this happens, and they don't discuss this in their paper, but this is sort of an interesting thing, I thought. But they have shaded this in the graph, but I couldn't find an explanation. But for some reason, the psychological sort of behavioral nudge really starts working quite well during Ramzan, I don't know why. And then people become very sensitive to or responsive to the psychological motivation treatment, and their labor market outcomes start to improve as a result of, because the psychological nudge treatment is very effective during Ramzan. But after Ramzan, it sort of goes back again and sort of no longer that effective when you want to rely more on, In fact, even the control group in which you do nothing, you probably want to allocate that with a higher probability relative to, the sort of nudge, and it loses sort of its effect. So I don't know if this is a coincidence, but maybe this is a coincidence because they say that the effect of the psychological motivation is short-lived. So maybe they started the experiment here, and it's just a coincidence that Ramzan was arriving after a few weeks, and they say in the paper that a psychological nudge only has a short-term effect. So maybe this is just a confounding kind of spurious correlation, or maybe something more interesting is going on. And the last sort of graph is, as I said, these assignment probabilities vary by X as well. So this is what is cool. It's the contextual banded. So for Syrian, F means female, SYR means Syrian, which is Syrian refugees in Jordan, and less than HS means their education is less than high school, and never employed means that they're never employed in the labor market so far. So they only measure characteristics on 4 groups, on 4 things, which are actually 4, all of them are dummy variables, because they just want to have 16 categories for X. Because if they have continuous information on X, then then it becomes even more complicated. So they just have 4 variables which are measuring the characteristics of people. All of them are dummy variables. And as you can see that over time, remember the purple color was showing the cash grant. Towards the end of the experiment, you want to allocate Syrian women who are less than high school educated and never employed with 60% probability. You want to allocate them to the cash grant. So I'm sorry that I've had this graph copied incorrectly, because I don't have the, I do have it, sorry. I do have the numbers. I thought I'd crop them out. So so you can see this is almost 60% or 58% or something towards the end of the experiment. So RCT would simply allocate all people regardless of anything, regardless of the treatment and regardless of individual characteristics, so 25% to all groups. But this algorithm takes account of the fact that the cash grant is really effective, because the Syrian women who are less than high school educated and never employed, really cash deprived and liquidity constrained. So we really want to, with a probability of 80%, remember you're doing Thompson sampling, which is maximizing the reward probability of employment. So these people towards the end of the experiment are allocating these kind of women who are Syrian, which means they're refugees, immigrants, and less than high school educated and never employed, with a very high probability they're allocating them to the cash grant, which was the most effective intervention that they found in this paper. So I'll end with an implementation in R. So I have some links here in which you can look at the implication of applications or in code examples in Python for contextual bandits as well as basic bandits. I'm not very fluent with Python, so I'm not going to do a Python example, but you can obviously have a look at these links if you want. In R, which is what I like to use, bandits can be estimated using what is known as including contextual bandits, but also non-contextual bandits. The package is just called contextual, and it estimates both contextual as well as non-contextual bandits for you. And I have the R documentation link here. And I just have a simple code for a Bernoulli bandit. And these are the probabilities. So remember, I'm simulating here. So obviously, I am trying to simulate so I know what the probabilities are. Of course, in practice, we are trying to estimate these probabilities. And that's the whole point, that we don't know these probabilities. So, but here I'm simulating in R, and this is pseudo code. So 0.7 there are 3 arms of the bandit, 3 treatments, 1, 2, and 3. The first treatment, the probability of success is 70%. And the second treatment, and for both of the other ones, it's 20%. And then you just have the contextual Bernoulli bandit function, which looks at Bernoulli bandits in R, and you give it input. You give the weights, the probabilities as inputs of this function corresponding to the column new, and then you use the Asians object, and you tell that you're talking about. So here I have 3 policies. I've implemented Thompson sampling as well as a random policy, which simply allocates probabilities randomly across these treatments. And then I have a UCB algorithm, which is the upper confidence bound. So I've implemented all 3 in one graph. So you just define these 3. This Thompson sampling 1 and 1, these are the alpha and beta, which are the hyperparameters. So this is not a contextual bandit. This is just a non-contextual bandit. Alpha and beta are just the starting values for the hyperparameters. And the fact that I've used 1 and 1 means that I'm using a symmetric beta distribution as as inputs. And then you just use a simulator function to simulate a 1000. 1000 is the number of simulations that I have. And each time I simulate for 100 horizon, 100 time periods. And then I just use a plot function to plot the cumulative regret. So if you don't use any option by default, it's going to plot the regret for all of these random UCB as well as Thompson sampling. And then the last slide, and this is just a graph that I produced yesterday when I was, when you implement the code that I have written in the last slide, this is the graph that you get. And as you can see that on the y-axis, you have cumulative regret over time, and 100 is the horizon. So you have time steps on the x-axis. These are cumulative regret paths. For the dark shaded line, I simply randomly allocate to the arms. And as you can see, I have a linearly expanding rate of regret path, which is really bad. For the UCB algorithm, I have something in the middle, which is sort of the lightest color here, lightest shaded color. I have a sublinear kind of regret, as you can see. But the Thompson sampling algorithm does even better because it is optimally allocating more often, in this case, to arm one, because arm one, remember, is actually the most optimal one. And the Thompson sampling is going to allocate with a very high probability. So it minimizes the regret in a better way. So that's it. We can have questions on the chat if you want. I am done, and thank you for your time. The part 2 of this lecture series will be conducted in January. In lecture so this is part 1 is ended now, and we have 2 more lectures, each for 2 hours again. In lecture 3, I'm going to discuss deep neural networks, which is in January. Your date will be communicated to you later. And lecture 4 is about computational linguistics and analysis of text data. And that is lecture 4. Both of these are part of part 2, which is in January. And the timings and Zoom links and everything else will be communicated to you later. You can ask questions if you want. Okay, so I think that probably. Yes, so I have been recording. Today I forgot to record for the first, I think, 7 or 8 minutes, but then I did record the rest of the lecture. So I have the recording for the first one as well. And we will, we will share these recordings, hopefully. So thank you for your time. I think I'm going to end the session. If you have more questions, then you can, okay, there is one question. I want to apply ML for financial analysis of energy markets. So it depends on if you have like, if you have data in finance. I don't know. I honestly don't know a lot about finance. But if you have sort of high frequency kind of data, which is sort of has a lot of volatility and that kind of thing, there are some methods that are used in time series forecasting for machine learning, but I don't think we've covered those methods. There is this thing which is called, I forgot its name, but there is this long short, there is this technique. I think it's called LSTM. But there are some time series prediction algorithms for machine learning, but we haven't covered those in this lecture. But so it really depends on the application. But I would advise that one should be very careful, and one should, because there is a tendency and there's a sort of danger that one can become too excited with these methods and just apply them sort of willy-nilly. And in lecture 1, I discussed the limitations of machine learning, especially for getting causal interpretations and so on. So if you are solving primarily a prediction problem with financial data, and your objective is to just get a very good prediction of energy market variables, and if you have a lot of data, and if you want to do real-time forecasting, for example, then maybe you could use some of the machine learning techniques in that context. But certainly, I think in most kind of finance applications, today's lecture is certainly not relevant for that. Today's lecture is sort of more relevant for, online dynamic experimentation, adaptive experiment allocation, and so on. So you can email me if you have more questions. I'm just ending the lecture now. Thanks. Thank you for your time and patience.